what we were doing, we had some x, which was we were talking about x, which was a moduli of vacua in some very supersymmetric quantum field theory in 2+1 dimension. And well, we didn't discuss this general notion in general, but we saw some examples. So e.g., we were talking about cotangent bundle to Grassmannian of k-dimensional subspace and n-dimensional space, or the Hilbert scheme of n points, k points in C2, and so forth. And so there are two general remarks about it. And one is this is always wants to be so we discussed with having one supersymmetry is like having the Raman operator, having extended supersymmetry is like having a Dalbo operator, and having this next level extended supersymmetry is to have it wants to be a hyperkähler manifold. Or which is a closely related notion, or a holomorphic, or maybe a holomorphic symplectic manifold. Right. And so this is one thing, and so this is clearly the examples we have here. The T-star Grassmannian is holomorphic symplectic just because it's cotangent bundle of something, and the Hilbert scheme that's famously holomorphic symplectic. And then so generally, if we talk about modulo of vacua somewhere, what are they? You have some all possible kind of configuration of fields. Now, to be a vacuum is a condition to minimize some function, actually. So, for example, in statistical physics context, Gibbs measure they minimize given functional, say, free energy with so that's among all possible states. And so this is typically so wants to be maybe or is or wants to be, well, I'll just write wants to be critical locus of some function. Right, so this is some configuration of fields. You have this function that you want to minimize to be in a vacuum, and then some of the configuration of fields may be a physical equivalent. That is to say, you're not really you consider you look at configurations of fields, and you divide out by some gauge transformation. So gauge transformations. Those are transformations that you declare to live to the same physics. There's some redundancy in your description, so that's a typical situation. And so then, if we have one such object, one can ask, what if I say, so what would happen if I perturb this function? Perturb. What's going to happen? So now, how are we supposed to perturb it? So if we had just a real manifold with the Raman operator, we could add arbitrary function, and there's a way to twist the Raman operator by an arbitrary function or derivative of an arbitrary function, and That's since you have an arbitrary function, it's like I mean, that's the context of Morse theory. Now, if you're on a complex manifold, then well, you have to add a holomorphic function, and then you're in the world of Picard-Lefschetz theory. Well, if you're on a hyperkähler manifold, then we'd like to add like a quaternionic holomorphic function. Well, that's not a way to construct this non-such or essential non-such with one exemption. So there's really there's one important exemption, one important scenario. Is the following. So I remind you that if I have a complex field, I'll write it phi have maybe has a real part, call it x, and imaginary, call it y. Then if I give it an ordinary potential, like a harmonic oscillator potential, so I'll write like m phi absolute value square over 2. One and I'm imagining that I have a symplectic form which is dx dy. Then one way to interpret this function, this is really the moment map. This is moment map. This is in the presence of that symplectic form. This is the moment map that generates rotations with angular velocity m. So I'll try to draw them here. So where m is this angular velocity, and maybe more canonically, you have you think of m as an element. You think of m as sitting in the Lie algebra of U1, which acts on my complex plane. And then this function is more canonical the moment map paired with that m. So moment map goes to the dual of the Lie algebra, and you pair, so that takes value in the dual of this Lie algebra. And so now suppose we have so we'll leave this for to be. Now suppose now U is a compact group that acts by automorphisms. Of X with all its structure. So for example, one way to encode it is to have a triple of symplectic forms, 3 forms that correspond. So if I have a hyperkähler metric, then the I, J, and K will give you 3 symplectic forms, and then maybe we can call this one to be the real. This will play a slightly different role for us for the reason I explained, and this together will be the complex symplectic form. This is the real, the imaginary part, and so then I have a moment map, which is right mu moment map from X to so I have 3 moment maps for these 3 things. So I have to go to the dual of the Lie algebra and denote the Lie algebra U. Tensor R3. This is where these three things live, and so this will be, so in this maybe I draw this picture here. So this is, we have kind of 3 directions of, but we maybe I'll draw. I'll try to draw a sphere where Imagine this is the sphere of complex structures, or and so this is this is a unit sphere in this R3 that I indicated here. So in principle, we have 3 different things, and we can pair it with 3 copies of let's imagine these are the 3 symplectic. Sorry, not like that. These are the 3 symplectic forms. All right, real, and then there's in this plane, well, like that. And so in principle, we have 3 components of this moment map, but what we would like, we would like to work equivariantly with respect to an action that doesn't necessarily preserve the hyperkählich structure, but rotates the sphere of symplectic form. In other words, we're working equivariantly with respect to a group that rotates the sphere around the vertical axis, the way I drawn, and that's actually the way. So this is extra U1 that rotates. This is the C star H bar. This is the one that rotates symplectic form, but it contains this U1 H bar. It's these rotations. And this H bar, the weight of this H bar is in fact, this is the deformation parameter around quantum group. In all these quantum groups that we would like to construct. So if we would like to preserve this equivariance, then we need to choose. So inside here, we have, we would like to pair it, rather maybe project it. So we'd like to pair it not with an arbitrary element, with the Lie algebra, not with 3 arbitrary elements, but an element that sticks into this real direction. So we would like to pair in other words, we take the function that is mu r paired with some element xi or m. So I previously denoted m, where m, so this would be our function. So m is in U. So, okay. And so then we have 2 options. So now 2 options. And we'll first explore option 1, and then explore option 2. And then in fact they're related. They're related by this 3D mirror symmetry. So option number 1 is we consider this U as external field. So that's just somehow. So this is i.e. global, some global symmetry which induces this correction to whatever potential we had before. And so then we have to look at the new critical locus. Then we only compute. This means the external field. Means we don't, when we compute the critical locus, we don't vary that U. So that we get the critical locus to be. So then we compute the critical locus along x of this function mu r m. Well, by definition of the moment map, the critical locus is where m x by fixed element. Right? So these are the fixed points. These are fixed points of the corresponding element in Lie algebra. And so this is, in other words, in our plane we have inside our space U. And for us, U will be, in principle, you can consider non-abelian groups, but we will consider abelian groups. You can always reduce to maximum torus if you want. So inside of this, there's some partition, where this extra fixed points arise. And so this is exactly the picture where you have the most generic stratum is the most generic stratum. If U is very, very generic, then this is so let's say U. Let's say I choose U to be inside the Lie algebra. I can always choose in the compact group. I can always choose U to lie inside of Lie algebra with a given compact torus. So then this would be, or which is a maximal torus. So actually, we denoted A, I think. So this Lie A. So this is inside A, which is the Lie algebra of A, and this is a maximal torus. In U. And so generically, we're going to get the whole fixed point, the whole fixed locus. This would be, if I have a generic element, that will generate the whole torus, and so this will be that. And if I have a very non-generic element, here the whole axis is fixed by this element 0, which just makes sense because if I take element 0, then this is a 0 function. Of course, the critical locus of a 0 function is the whole of x. And so going back here to this picture I had, what would happen if m? So what would happen here? There is a wall in the space of all possible m's. So we had this was m, and so well maybe I'll I invert the direction of this m line, and so that was the picture where m is positive. There's also a situation when m is negative, and then this, of course, this picture exactly reverses, and so your potential will start pointing downwards. Right? And then there's a middle case where your function is just 0. Function is just 0. And so just looking at this picture, we see here we have this particular complex direction is attracting, means here the force induced by this potential forces the field to go to 0. This complex direction is repelling. This is the force induced by this potential makes the point go away from 0, and there's nothing, it's neutral, nothing going on here. But since this is a moment map, this green arrow, this is the action. So this green arrow, this is the action of the complexification of GL1, which is the complexification of. So you complexify this U1, and so this says from the point of view of a compact group, somehow nothing happened, nothing really changes. Is you were rotating one way and then you start rotating the other way. But from the point of view of complexify, you see the difference between attracting and repelling potential, namely either this whole direction of phi is contracted to the origin or expelled from the origin. And so then now we go here, and then these different chambers that we see here, this correspond to different choices. So so this is maybe, let's consider this two extreme situation. When the function is just 0, the function is very generic. So these are different chambers. These are different attracting repelling directions. So this would be maybe I'll write this A compact, this compact torus for the whole torus of A. So A is a complex torus, and so then it's some directions. This means as I vary this parameter m, then some directions go from being attracting to repelling. Well, and since we decided the torus acts, since this I remind you that this torus acts. This torus acts. Maybe I'll put it here. Since A acts preserving the in particular the holomorphic symplectic form, attracting and repelling directions are always paired. So you get the same number of attracting and repelling directions, just which are attracting, which are repelling. That changes. And so then what we would like to have, then of course clearly we would like, remember we decided that if you have some external field and then that external field goes through some critical value, then that means you get kind of more physics at the critical value, less physics at the actual point which you were I apologize for 1 sec. I forgot my cup and I want to take a drink of tea. All right, so we would like the interface, and what we would like to have we would like to have an interface, which is in this language. We would like the interface to be between these two things. So that would be ideally would be wants to be which wants to be between x and the fixed locus wants to be first wants to be a Lagrangian submanifold, a holomorphic Lagrangian submanifold. So this is a little bit of wishful thinking, because so if you think this all your moduli spaces are smooth and everything is smooth, then you'd like, well, if my moduli space is some hyperkähler manifold and a natural correspondence between them is a holomorphic Lagrangian, is a holomorphic Lagrangian variety. So okay, maybe this is a little too much to ask, and we'll see this really too much. Why is it too much in a second? But also wants to be, and also, which it looks like. Which looks like the attracting manifold of XA in X. So if I turn on the potential, every point will start experiencing a force, and that force will drive it to well, either drive it away or drive it to a particular fixed point. And so what we would like is to have this correspondence where a point is driven to a particular fixed point. Well, like I said, so this is a little too much, because if I consider this attracting manifold, this is in general some, well, it's either as defined, this would be some locally closed set. If I close it, this will be some very singular variety. And so this, in fact, so this would be, this whole theory of stable envelopes is precisely addressing, so kind of stable envelopes. This is precisely answer somehow construct. This is really how this is kind of these are good correspondences that come as close as possible to this goal, to accomplishing both of these goals. So that's really like, and this, the actual nature depends. So this is when you can't really talk about the manifold anymore. The actual nature of this will depend on which cohomology theory you're talking about, and so we will eventually eventually I think we'll focus on elliptic cohomology. We'll have to, it will be the most natural. But then remember, here I stated option number one, and so now option number two, of course, is we can declare instead of considering here we took a symmetry and we declare it to be just like an external field. Instead, we can declare U to be add U to gauge symmetries. And so this means that first the fields we consider, they no longer fixed, they're allowed to vary. So in particular, when we compute the critical locus, so so it means we compute the critical locus, to compute the critical locus of the moment map paired with M with respect to X in X, maybe I'll write mu of X, mu of X paired with M, and that M this is an element in U dual 3 copies of it. So there'll be, these are super partners of our gauge fields in both X and M. And so then this means the equations we get. So this means the equations we get not only that M fixes, all three M's fix X. So M fixes X. Okay, this is one equation, but we also get, if we vary in M, we also get that both the real moment map is 0 and the complex moment map is 0. So this means this is part one, and second we take the quotient by U, and so then it means this procedure is called, we go from X to hyperkähler quotient, and different people use different number of slashes. Since we take out, so this means you take out how many? You take 4 times the dimension of U, since you pose 3 times the dimension of your equations, and you divide it by U. And so they already has 4 slashes. So this is, people call it hyperkähler reduction. Kähler reduction, or holomorphic symplectic reduction. And then in this process, there is in fact a degree of freedom, Namely, if our group is, for example, is abelian, or otherwise has a center, we can so there's a generalization here. One can more generally or make this real moment map take a value theta, which is, so the moment map is only defined up to a constant, and that constant could be any element we want in the invariant part, in the center, in the dual. So you make it to be in the invariant part of the dual of the Lie group. So this is like, for example, if you're taking quotient by GLN, then the GLN has a one-dimensional center, so you get 1 degree of freedom here. Okay. And then this corresponds to the fact, so then this corresponds, so when we put this theta here, and that theta corresponds to a choice of, in the holomorphism flash reduction, you get a choice of polarization, that is this choice. And so now, now the kind of the dual part is that is the dual, you know, instead of M line, you get this kind of theta line. And then when theta, so maybe maybe there's some stratification of these thetas. Where you get different, so how this quotient depends, how this theta, well, how the quotient, how the theta stable locus depends on theta. This is also described by some stratification, which is superficial, just like that. And so then if I have some maybe generic theta and some less generic theta 0, then the stable locus, if I look at the theta stable locus, this is a subset in theta not stable locus. So this is again to the goes to the underscores the point that if I have a generic value of external parameter or specific value of external parameter, then I get, so this is now, this theta is now my external field. This is now an external field. And then I would like a corresponding, similarly a corresponding map on whatever, some cohomology, some K theory or some cohomology or K theory of something. I would like it to, so analogous to what we had before, we would like a map on, a canonical map, a reasonably canonical map, a good map on, say, K theory. You can also categorify it if you want, or elliptic cohomology, or something. So the reason we don't talk much about categorification in this course is because we started with some quantum field theory we didn't know much about, and then it flew to particular one we're studying, which is like maps to the modular spaces of vacuum. And you can analyze that theory in much detail, but that would be, but if you could take, well, the only thing which is deformation invariant is K theory. And so if you deform away from this particular theory we're studying now, then the categorification is lost, or at least will be probably lost in most cases. So, and so then, well, anyway, and so then what will transpire? So then, we will find out the two things. That one is this not really different from stable envelopes. So this is the really objects of the really exact same kind, and you can just, you can reduce one to the, you can reduce one problem to the other, or the other to the one. They really belong to the same universe of problems, and also it's really mirrored rule. Part one. All right. Okay, so now we would like to so address the following general problem. So general problem. Some x would be x is an algebraic variety. With some assumptions, we will make say smooth singular algebraic variety. With some assumptions, perhaps perhaps homomorphic symplectic. So forth. And what we would like to have, then we have an action of a torus A, and we would like to have for every we look at the Lie algebra of A, we find in the Lie algebra of A we have this diagram. Namely, we look at difference. So if I have over a point little a here, I see, well, if I have a point A here, I can at that point consider the fixed locus by A, and then it jumps. So let's say A be a torus, right? And we would like would like somewhat, the nicest possible. We want possible map from the K-theory of the fixed locus. Let's consider maybe extreme situation. So here I have my fixed locus of all of A, and then here sits the fixed locus of some subtorus, and here sits all of X. But let's start with this, the most general situation. We'd like to go from this way. What we would like to have a map from the K-theory of the fixed locus to the K-theory, like particular isomorphism between this and the K-theory of attracting manifold of the fixed locus. Well, the attracting means we consider all points. These are all points that by the action of a one parameter subgroup corresponding to, so there's a certain cone, we call it C. So choice of a cone in this picture is a choice of attracting and repelling directions. So attracting with respect to that cone. So it means if I consider a general one parameter subgroup in that cone, and I'd like that one parameter subgroup to take my, so maybe I'll write definition. So this is the set of pairs. I consider a fixed point and consider a point X such that the limit of, I take some one parameter subgroup, call it sigma, of some variable, call it what's a variable, call it I don't know, U, acting on x equals f, u goes to 0, and sigma is a one parameter subgroup in that cone. So sigma is a map from C star to A, and this sigma is in my cone. So so we will like abstractly this set is isomorphic to, well, we'll see abstractly that this is isomorphic. We would like particular one, and in particular we would like it to be equivariant with respect to the centralizer of A, equivariant with respect to the centralizer of A in automorphisms of X. So this is like to regain as much equivariance as we want. So in particular, this would be in this automorphism of X, there will be some element that scale my holomorphic symplectic form, act by this with weight h bar in this holomorphic symplectic form, and those would be that h bar would be a variable in here, and this would be this exactly parameter deformation, and so this of course, this is not just for K series. This would like it for ordinary cohomology equivariant, for elliptic cohomology equivariant, and so forth. You can also do dB coh. So in principle, you can study this in many contexts. And so then what was special about the examples we considered before? So in examples like X being T star Grassmannian k-dimensional subspace and dimensional space, so there was this action of GLN of the Cn, and A was sitting in here. And so then what the special effect thing that happens then, all these fixed loci, they all products of varieties of the same kind. Right? And so that means that this map, which the map should exist in general, but in particular in the situation we have in the situation when we want an action of a quantum group, then this K theory will in fact be a tensor product of a bunch of things of the same nature, and this what makes this like a braided tensor category like we discussed last time. This map. And of course the property that we want is like I said, the analog of Young-Baxter equation, which is just what would give you. So then since this is a product, means the K series will factor. So this means this will imply that the K theory of the fixed locus, that's really a tensor product of K series of some other x's which are just kind of just like that. And so this would give you this gives me this tensor product gives our matrices. But in general, there's still a structure, but it's just not a structure of a quantum group. It's a structure of some more general algebraic structure. And so then what's Young-Baxter is supposed to do? The Young-Baxter follows from the property that we want, namely that if I have my x with fixed locus with respect to the whole torus, and I have a fixed locus with respect to a subtorus, and then I have my all of x, then I would like this maps to commute. This triangle needs to commute. So these are all instances of the same problem, and this if all these triangles commute, then this gives you Young-Barkster. Okay. All right. So that is let me look at my notes. I look at my notes. And so all right. So now we have to talk about, since this is supposed to be a very pedagogical course, then we have to talk about what are the cohomology theories. So this will occupy it for some time, because, well, I mean, to construct the map, you need to understand the source and the target of this map, and it's some kind of K group here. So this will be what will occupy us for some time, is discussion of equivariant cohomology theories. And so the examples, in particular, the examples would be ordinary equivariant cohomology, then the equivariant K theory, then equivariant elliptic cohomology, and in principle, there's a mother of them all. There is equivariant cobordism. This is the mother of all these theories, and then I'm very happy to announce that next time we'll have a very special event. We'll have a guest lecture. So next time, guest lecture by the best possible person to talk about, our very own Igor Krichever. So this would be this is, well, that's I'm personally very much looking forward to that. But we're mostly interested, well, for the purposes of this discussion, we mainly interested in elliptic cohomology. And the reason we're mainly interested in elliptic cohomology is because, well, it's because if I have, so remember we have this kind of Riemann surface, and then we had some parameter, and that parameter will reach a critical value along some circle, well, not circle, I mean a union of circles in general, but so I'll draw it like that. That's where that interface lies. But then if we take the time direction, so with the time direction, and remember, when we compute the index, we make the time periodic, and so that's really this really means that this we identify this with that. These two are identified. And so you see an elliptic curve in front of your eyes, or a torus at least. And so this interface is really something that lives. This interface is some other quantum field theory, which really lives on this torus. And so this is why elliptic is kind of the most important for us. But it's a little difficult to explain what this elliptic cohomology is. I believe it's easier to explain the two things. It's easier to explain, but certainly easier to explain what's equivariant K theory. So this will start this today. This is beautiful and concrete. I mean, all of these theories are beautiful, but this is very concrete. And we will start with that. And so and that will hopefully discussion of this and of K-theory and cobordism will together prepare us to tackle the elliptic homology, which I admit if you ask for your money back for so I'll be very happy to issue a refund for those disappointed in my treatment of elliptic homology. Well, it's really a very deep subject, which has to be done by trained professionals, and I'm certainly not one. So this is a subject of a whole different set of lectures. But we will make an attempt to discuss what this is. By contrast, so K-theory, equivariant K-theory is something, like I said, it's something extremely concrete. So it exists in many incarnations. Maybe the easiest is the topological K-theory. And for varieties, actually, I want to say that from the very beginning, for varieties like the Hilbert scheme of points, or the Grassmannian or Nakajima varieties, all varieties we're going to consider, algebraic K-theory and topological K-theory are the same. So you can think about one way or think the other way. So that doesn't really matter. And so in topological K-theory, you take a compact group acting on a space, which is general topological space, but to start, it's convenient to assume compact right now. If it's not compact, then there's a slightly more complicated discussion. And then what's KG? An element in KG is just a G equivariant vector bundle. So it means I have an X compact manifold, and the G equivariant bundle means a vector bundle on which there is an action of G lifting the action of, so it means if I have some fiber, so this is a vector bundle V, so it has a fiber X, maybe E, call it E fiber or X, and then there's a GX, so there's an element G acting here, so there's a fiber GX. And then it's required that the group also acts on vectors. So if I have a vector in here, that's taken by the action of my group to another vector there. And this is a linear map. This map is linear. And in other words, if you have a vector bundle is a manifold that maps to your X with fiber linear spaces, and you require that the transition maps are preserved as structured, they act by linear maps. And similarly, when you take a group action, you require that action to be linear. So this is like a representation theory of G, except you don't act in a given vector spaces, you act in a fabulous vector spaces indexed by some label X, where X belongs to some set on which group X. So this is supernatural from the point of view of anybody who ever thought about representation theory. And so this have the operations. So if I have two vector bundles, I can consider their direct sum and the tensor product. So this makes the set of G equivariant vector bundles. I guess it's called a semi-ring. It's a set where you have addition, multiplication, but you don't have subtraction. And then the K group of this is when you take that and you add the formal inverse, add the minus operation. So this is formal difference. Again, in representation theory, this is very familiar. If I have a virtual representation, that's a difference of two representations, and And so then, in particular, the character of a difference, well, the difference of characters. And so what I'm trying to say that if X is a point, so a point, that is just a representation ring. Ring of G. And so, and by pullback, every map maps to a point. There's a pullback of vector bundles. So this equivariant K theory is contravariant. It's a cohomology theory. Means if I have a map, if I have been mapped between spaces, then there's a pullback. Then the pullback. So in general, so maybe equivariant K theory is contravariant. I'll just write it. Contravariant with respect to maps. So in principle, you have some group G1 acting on some space X1, going to some group G2 acting on some space X2, and where this map, this is a group, where this is a group homomorphism, and this group preserving action. So this is the, so if I have a G2 equivalent bundle over X2, and then I can certainly pull it back here, and so that would be clearly a good operation. And so in particular, every space maps to a point that every K theory is an algebra over, so that means this is an algebra. It's an algebra over this kind of base ring, the K friend zero point, which is what is it? So we're so in general, this is representation ring. So these are the kind of integer valued conjugation variant functions on G, right? But we're mostly interested for abelian groups, This is just G. This is just functions on G. So in other words, this is K theory is some if I look at the, in other words, if I look at the spec of equivariant K theory, and this we will have to be doing this. So because when we start talking about elliptic homology, there will be no rings anymore. There will be just schemes. So there will be no. Well, it has to talk about spectrum in the sense of algebraic geometry, not also in the sense of different sense in topology will also appear. But let's just the spectrum of this ring. This maps to the group G as somehow it's sitting over integers. It's kind of a constant. This is like a constant group scheme over integers. So that's right. So this was the topological case here. Now there's algebraic versions. What we can do, we can consider vector bundles in algebraic geometry. And then, or we can so what would be, so that's one option, but actually a better option. In algebraic geometry, there's a more flexible object. We can consider coherent sheaths, G equivariant. So then in general, there's a similar definition, what it means for for a group to act on a coherent sheaf, but maybe very prosaically, if I have a coherent sheaf, so all of our schemes will be, so coherent sheaf means we have a sheaf. Coherent means it has a finite presentation, so it has finitely many generators. So F1, so these are the generators. It's a module, as a modular function is generated by finitely many things. So this is a free module of some finite rank, so that's free. And then all of our schemes will be Noetherian, so automatically this would be also relations would be finitely many relations. So why did I write 3 relations? Relation. And these are, well, guess what, are both local, not free, locally free, both locally free. Both of them locally free. And so the group just really, and you can say the group really acts here. The group, what does it mean for a group to act on the module? Well, it takes generators to generators, relations to relations. And you can say it like that. So you can choose a resolution which is equivariant. So that's, but you can of course read the definition of what it means for a group to act on the coherent sheaf. And so now what is it, what are the, so this we will denote this. So we will just denote K theory, G equivariant K theory of X. We will denote what you get from coherent sheaves. In other words, as the Grothendieck K group of the category of the coherent sheaf G equivariant coherent sheaves on X. And what does it mean, a K group? It means if I have an exact sequence, all right, G. Why? This is probably confusing if I denote it by G, let's denote it by E. So if I have an exact sequence with a sub E1 and a quotient E3, then I declare that the class of E2 in K theory is the sum of E1 and E3. And then, so this would be denoted, we will use this notation. This would be for that. And this would be denote K-perf when we need it. So, so this, since what's generated by locally, well, that's the, and a kind of basic fact in algebraic geometry that if X is non-singular, then the two are actually equal. It's very important. Means every coherent sheaf has a finite locally free resolution. That will be. All right. So what are they? So this is supposed to be. So K theory is supposed to be a functor. And what are the factorial properties of? So if I have a map between algebraic varieties, X goes to Y. Then there are factorial maps. And K theories, well, kind of can, well, let me explain. So so actually, following classics, it's very convenient to factor this map into two spaces, into two steps. So if I have the map like this, I can factor it as an inclusion of the graph. So maybe call it the graph. There's a graph of my map. So this is the graph of F, which is the set of X, F of X. And so then there is there's a map from this which is an embedding, and then the map to Y, which is the projection. maybe call this iota, and call this pi. So then if I let's start with push forwards. So if I have a sheaf on the push forward under iota of a sheaf on X, well, it's just, this is extension, it's just extension by 0. So this may or may not be a graph. I mean, just inclusion outside the image, outside the image. So that's a very kind of very easy operation, and it's yeah, clearly, and so that's, you don't need, you have a sheaf, you just make all functions the ideal, your new sheaf, you make the ideal of this graph act by 0, and everything else you act as it was acting before. But then if I push forward something, so this is, maybe I have if I push forward some sheaf, let's just now this point G. So now if I just push forward sheaves in just consider the sheaves push forward. So maybe I'll write the class. Maybe the class, I want to push forward the class of G. This would not be correct. So this would not be the same as the class of the push forward. Well, because if I have an exact sequence, then this will, if I push it forward, it will cease to be exact. And so the right thing to say is to put count all cohomologies. So you put you don't just count sections. You count first cohomology, second cohomology, and so forth. So you count. So this becomes summation minus 1 to the I. You take the class of the higher derived functor, the cohomology of that sheaf. This is for cohomology, higher cohomology. And then this makes this is now this now if I have an exact sequence of sheaf and I push it forward, then by long exact sequence in cohomology, I get that this is a correct operation on K groups. And so then what do we need for this to be defined in K theory? We would like this sum to be finite, while we will for now we'll consider finite dimensional varieties. So this would be finite, is bounded by dimensions of the variety. But this would be important. For this, we need to be coherent, or at least so. And the way to guarantee it is that this is guaranteed by, this would be implied by F being proper. So if I have a proper map, then this would be this by general theorem of classical algebraic geometry. This would be a coherent sheaf, and so I'm good. And so and also I want to say that two things, that in general, if I have even if I'm pushing forward a vector bundle, there is no reason for the image to be a perfect, to be in K-perf. You have to assume further things on the map that land in K-perf. So, but on K theory of coherent sheaves, this is once the map is proper, then you're now this works good. But in equivariant, so actually in equivariant theory, may be relaxed. Namely, if you have In equivariant theory, you can have a graded, an infinite dimensional representation, which is still has finite multiplicities. So if I consider, so in other words, you can have an infinite dimensional module with finite group multiplicities. And in the simplest example, if I consider the map of a line, a fine line, so let's call it, A1, just map to a point. And what would be that? So if I have my coordinates, say x here, then so maybe the map, and the push forward of the structure sheaf of my affine line, well, that's all polynomials in x. So, forgive me for writing C of x, whatever field we had. And so this was if I had an action which scales this A1 with weight t, then this has character. This has character, which would be, well, the weight, if I act with weight t on a fine line, then it acts with t inverse on the variable x. And so this has character which is equal 1 plus t inverse plus t minus 2 and so forth, which is, it's a well-defined expression. And so, what you really need is, well, not really need, but what suffices to assume, for example, to assume in G. You can make bigger assumptions, but as soon as assume that thing is contracted, that thing is contracted, can be contracted to a proper subset. This is contraction means you have a choice of, like we discussed before, the contraction means you have a choice of some attracting direction, repelling directions, and that choice will tell you in which way, like if you want to multiply infinite series, you have to make an assumption as to which way the coefficients go, and that would precisely the fact that here I get only this is an infinite series, but it's okay as a series in T inverse. This is because if I act by T, I contract everything to 0. And then right. So now going back to again to factorial properties of K theory, then we consider pullback. So we had we consider pullback of some vector bundle E. Well, that's just pullback. With this is since we're means you have a this is a projection. You had something on the base. You can just you have a sheaf on the base. You just pull it back to the total space of the projection. So that's not so complicated. But now if I want to pull back something with respect to the inclusion, what was that? Some sheaf G. So then the pullback of this class, well, I can't really. So this would be wrong to just pull back the sheaf. So for example, suppose I have two lines on a point, two line and some like if I have a line and I have a point and I have another point, then all points on the line are equal. Structure sheaf of all points on the line are equal in K theory. But then if I really pull back the sheaf here, well, it depends where I pull back to the same point or to a different point. And so that would be so this would be again, this is not the class, the pullback here. What I have to consider, I have to take all the higher torus. So this is summation -1. So this would be so this would be So this naive pullback is I take, so this guy here is I take my sheaf and I'm tensor it with the structure sheaf of my graph, which is not an exact operation, but what I have to complement is with all the higher tors. Sorry. And to compute it, you resolve one or the other. Resolve either of them. By local free sheaf. So this is computational. You have to take a resolution of one or the other, and then you tensor the resolution, and you add this corresponding tensor factors. And so in particular, it's always, so then the issue is, when is that sum finite? And so then you have to either, you have to make some assumptions. Is there a question? You have to make some assumptions when is this to make, so we need want to have it well defined. We want this to be finite. And for this, we have to make assumption either about the map or about the sheaf. So for example, if I pull it back locally free map, then locally free sheaf, then I just pull it back. So that's good. And I mean my locally free resolution is just one term. And or if my map is flat, has, or at least has finite tor dimensions, so I have to make some assumptions here. Again, equivariantly may be relaxed. So equivariantly. May be relaxed. Like EG. So if my x is like the simplest possible single variety, xy equals 0, and then my sheaf is let's say, so my interest in the sheaf, which is like the structure sheaf of the origin. So that, of course, this doesn't have, since x is singular, then this doesn't have a finite local resolution, but it has so this resolution has infinite resolution. But that resolution, again, if you think of this, how the group, so maybe the group acts by, in fact, there's a two-dimensional group acts here, but let's for the sake of the argument, let's assume that you scale both of them by maybe, well, okay, you scale both of them by different things. So this is this infinite, the character of this operation, but this is well defined. This operation here is well defined. So imagine I'm trying to pull back the origin to the origin. So it means I need to find this resolution and then tensor it with the structure sheaf of the origin and see what happens. But then this is well defined, and the reason this is being well defined is because can be contracted to something smooth. So if I have a smooth algebraic variety, then every sheaf has a finite local free resolution. If my variety is singular, that's not the fact. But if it can be contracted, then equivariantly it can make sense of that. All right, so that's a good exercise to do, and maybe let's start. So this is every course that discusses equivariant K theory, I think, has to compute kind of the main example. So we will compute one to compute. If you've never seen this before, and I'm only explaining this on the level. I apologize. I'm not the greatest possible what's the word? I'm not the greatest possible sorry, my English word escapes me. So I'm not really doing justice to the beauty of the subject. And incidentally, there's an excellent exposition of equivariant case here, which I really recommend. So excellent exposition. There are many excellent ones, but expositions of equivariant case here. Of course, you can read Thomason, of course, but if you want sort of something very accessible, this is, for example, chapter 5 of Chris and Ginsburg. Or Merkuryev in Handbook of K theory. I don't know why I wrote him as if it's a K theory class, but so anyways, this is I really recommend you read something more professional. Let's see, my goal, my kind of another goal in this lecture was to compute the equivariant case theory of projective space. Let's see, I have 6 minutes left. Well, let's see. So maybe we'll at least illustrate some very important. We'll start this computation. So we'd like the GLV equivariant case theory of the projective space associated to V. So this we would like to compute. All right. So how do we gonna approach this? So this maybe I will start with discussion of the first 2 steps of this are very, very general. So what is projective space? Projective space is, after all, the quotient of, you take V, take out the origin, and you mod out by GL1. So this actually, this may be my, well, I don't know, not mine. I subscribe to the point of view that the equivariant homology theory are simpler than non-equivariant ones, and the reason being is that most important varieties like projective spaces, Grassmannians, and other varieties that appear in everywhere in geometry, they are quotients, and so if you want to access their cohomology, then it's very useful to exhibit them as, to use this, because one principle of K theory, that if I have a quotient, so if I have a quotient by the group, this is let's say it's a free quotient, or so let's say, so this is a free action, and I have a quotient, then there's a map from X, from the pre-image of that, and I claim that the ordinary K theory of that is the same as G covariant K theory of the pre-quotient. And what are the maps? Maps are this map this way. So this is the map here. So this is isomorphic, and this map here is by pullback, and this map here is by taking invariance. So that's in fact these maps are in fact equivalences of categories. So not just K groups, all the higher K groups are the same. So, and so the first step is that we identify this. So this is kind of important. So also identifies all high K groups. We're not going to talk more about high K groups in this course, but and so so that's important. And so this is the same as you take GLV cross GL1 of V, take out the origin. That was the first step. And where's the GL1 acts, it just really acts as a center. And here we consider it a separate group, but it's really, kind of it's the center here. So this is how it acts. So this is, so that's kind of, so maybe that was my one important point about this computation. Now comes the second important point. Suppose I consider the complement of some subvariety. So behind me, you see this is kind of maybe what's supposed to be the most important discussion of this class, but so cohomology theories in general, they supposed to take certain sequences of spaces to long exact sequences of cohomology groups. And so there's the incarnation of here. So if I have X, so in general, if I have X, and I have a closed subvariety on X, so this is closed. Closed G equivariant, G invariant. And then similarly, there is an open. And the exact sequence in K groups, the way it starts is that first the G equivariant K series of X surjects onto the G equivariant things of the open. So it's a basic thing that if I have a G equivariant thing on the open, I can always extend it to the closed. So you can prove it as an exercise, it's not hard. And another exercise you can do is that the kernel of that map is really so this sequence is exact. So this is the kernel. If I restrict to the open, then the kernel. So this map is by restriction to the open, and this is by push forward. Observe that this goes in the direction opposite to how a cohomology theory would be. So in other words, the K theory of coherent shape it behaves more like a covariant theory than contravariant theory. And so this is, and so then this is of course not included. There's a as you can see on the picture behind me, there's a K1, which is in principle, see it's here, and so this is how the long exact sequence of K group starts. And this is, again, that's an exercise you can do. And so now we come back to this question: is that the so we have a closed which is 0, and we have the open, which is we consider here. And so we have, therefore, we have identified the GLV cross GL1 equivariant K theory of V minus the 0. This is the co-kernel of the map. Take the equivariant K theory of V cross GL1 of V. So this maps here. And then there is just a point. This is the inclusion of the 0 is just a point. And okay, we're ignorant about what comes here. We don't worry about that. And so this object is a co-kernel of this map. So this Sankey was the second kind of important point. So this long exact sequence, very important. And so now we have to compute the co-kernel of this map, but there's a third important principle that if I have a vector space and I consider equivariant, so think about it, so here I have a vector space and I consider sheaves equivariant with respect to in particular the scaling action on my vector space. So then every such sheaf is, first of all, can be resolved. So these are, it's equivariant. That means, first of all, it can be resolved by free sheaves with some group action. And then a second, that free sheaf with a group action, it just what it determines. The only thing that it remembers is what it does at the origin. In other words, there is a map, maybe more canonically, since this is a vector space. And moreover, it's not just and it's not just some arbitrary vector space, but in fact I do it. I consider things equivariant. So this means this object here means I consider graded modules over polynomials. Any such is, so what I was trying to say, the way you resolve any such is that the opposite map by, if I consider the map, there's an opposite map, which is, so not the map, it's a different map. So there's a map by pullback. So if I could, this is the push forward. There's a push forward map. But there's also the pullback, which is, so there's a projection here and just pullback. And so that is an isomorphism. And so we now reduce to the fact that we want to do that so this is kind of the third kind of important thing. And so this reduces the fact that we want the computation to that if I want a GLV current here of projective space, that is the co-kernel of the map. I take this kind of point. Maybe I'll abbreviate this group to G. To the same, kind of the same, abstractly the same, but where this is the inclusion. This map is the inclusion of 0 in D. And now this is the third step, and now I ran out of time a while ago, and that the most beautiful step is that there is a classical resolution. You can use Kuzel resolution. So this is Kuzel resolution. And we do it. So this is super important. Inclusion. So if I want an inclusion of a point in a vector space on a general manifold submanifold, this is super important. This we will go. Although I imagine most of you know the subject better than I, but since this is supposed to be a pedagogical thing, this will do next time. Well, not next time. This is due in 2 weeks. So next time. Don't forget, guest lecture. Bye, Igor. All right. Well, I was full of good intention to finish on time, but I apologize for running over time. Are there any questions? Well, if there are no questions, then I thank you for your patience, and I appreciate your
question.
Sure.
What is the analog of K-theory on the mirror side? Would it be quantum cohomology?
Well, they all take place. No, the K-theory, they all take place. It is still K-theory, so it's just you add more. So you get more when you talk about, like, say, quantum K-theory. It's just the same old K-theory to which you add more variables, and that which remember the degrees of the curves, and so then it's those variables that get permuted. So there's some identification of these two things between two mirror sides, but you can still compare